Okay, the last video stopped right before I was going to end this video, or the previous video. Last thing I was just going to say is that here we have quite a bit of resonance. Here we have zero resonance. So that's why we expect such a large pKa difference, okay? In this case, we share the best resonance structure, okay? Delocalizing that charge across our highly electronegative oxygen atoms, okay? Yes, you could say this one has a lot more resonance structures, but when we do that, the best resonance structures we get is disrupting a benzene ring, and we're getting negative charges on carbon atoms, carbanions, not the best, okay? So yes, there is more resonance, they're just not great resonance structures. So yes, we do have a lower pKa, but not as drastic difference as our example on the left, okay? So textbook just wants students to acknowledge that not all resonance structures are equal, okay? Again, we're sharing the best resonance structures here, and the difference in pKa is from our other resonance structures that we could draw with our carbanions. Last thing I was going to say there. Okay, now the rest of this, real quickly, we're going to go over proton transfer examples, okay? So pause the video, work these out, okay? Draw arrows, label acid, base, conjugate acid, and also draw which way the reaction will be favored, okay? Pause the video, try these 4 out. Okay, top example here, my base, pretty easy to find, has a negative charge explicitly drawn. I have a hydrogen explicitly drawn, that's my acid, okay? I have a lone pair from oxygen, not my negative charge, my lone pair that will attack that hydrogen, okay? On an exam, I would rewrite this as that. That way I can show that bond explicitly go onto oxygen, okay? Those are my 2 arrows. My products then will be butanol and this guy, okay? If I wanted to draw lone pairs in there, I could. All right. This would be my conjugate acid, okay? My base always turns into my conjugate acid, conjugate base. Now let's compare pKa values, which you have memorized, okay? pKa value for carboxylic acid is around 4. For alcohols, it's around 16. So which way will my arrow go? Okay, it's going to go from high to low. High to low. This reaction is going to favor the left to right direction. Okay. Stronger acid's going to dissociate more. Those hydrogens, think of them as going in that direction. Okay, equilibrium. Awesome. Next example. I have a negative charge explicitly drawn in. Okay. Base, acid, lone pair here on carbon, same as before. Okay. Gives me a nice benzene ring with no charge, and this species here. Okay. Awesome. Okay. My base is going to turn into my conjugate acid. My acid will turn into the conjugate base. And to compare it, to see which way this reaction is going to be favored, let's compare pKa values. Okay. pKa value of alcohols is about, again, 16-ish, 15 to 18. And then my benzene ring here, alkenes, if you remember, alkenes are about 35, okay? 35-ish. I feel like benzene might be different a little bit. Maybe between 30 and 40-ish. 35 is good enough, okay? Clearly shows that we are almost 10 to the 20 times more acidic in this position. Again, this is going to go in the left to right position. favor the reaction that way. Okay. Let's keep going. Okay. Base, acid, thiol there, benzylic. Not in the benzylic position, but maybe just a benzyl thiol, perhaps. Let's draw my lone pair on hydrogen, the only electrons it has. Okay. Remember, sulfur is in the same column as oxygen, so it's following a lot of these examples. And that we're having a negative charge on our sulfur, which is not too bad. And hydrogen gas. Okay. Acid's going to turn into conjugate base. H2, which I don't know the pKa value for. You aren't expected to either, but we could find it out real quick. Perhaps. My phone's taking the video, I can't use my phone. Let's say it's probably very high. I would imagine you have hydrogen gas, like how willing is a hydrogen gas diatomic molecule going to give one up and turn to H minus? Not good, okay? We don't even really need a pKa value there to know it's not good, okay? So we're just going to call this high, okay? So high pKa value, very weak acid. We have a thiol here. Now, again, we don't know the pKa explicitly, but we can reason it out, okay? Thiol is it's similar to an alcohol, only we're using sulfur, which is right below oxygen in their periodic table. So they have similar chemical properties. Sulfur is larger. When sulfur loses a hydrogen, or loses an electron, it's gonna better be able to deal with that negative charge when it turns into a conjugate base than oxygen would, okay? Our cardio rules, remember, as we go down the column, our larger atoms are those that are more stable as a conjugate base because they're larger. So, will we expect a thiol to have a higher or lower pKa than alcohols? We would expect thiols to have a lower pKa than alcohols, okay? Because sulfur can deal with that negative charge better as a conjugate base, making it more stable, aka weaker, meaning a stronger acid. Stronger acid, lower pKa. We would expect thiols to have a lower pKa than alcohols because they're more stable as the conjugate base, and thiols happen to have around 10 pKa, okay? So about 10 to the 6 times more acidic than alcohols that are about 16. So thiol here is about 10. You could just reason it out as less than 16, okay, because we know thiols are stronger acids. So we have a strong-ish, and it's still a weak acid, but a much stronger acid on this side of the reaction arrow, a much weaker acid there. Again, this is going to follow the left to right direction. Make some room here for our last example. Okay. Nitrogen-containing compounds are almost always they're very commonly bases, unless we get something like NH4+, okay? I have an alcohol here with the hydrogen explicitly drawn, okay? Acid, base, lone pair on here on nitrogen. We'll accept that proton, the oxygen there, okay? Triethylamine gains a hydrogen and a plus charge. And then I have this negative charge. Okay, awesome. Let's do pKa's. Alcohol here again, that's about 16. Conjugate base, conjugate acid. Okay. NH group. this isn't going to show up on an assessment, okay? That charge is kind of funky. Let's instead just assume that this has a similar pKa to amines, okay? Let's just assume that for sake of argument. What's pKa of amines? If you said 35-ish, you're right, okay? So which way would this reaction go? It would go in that direction once again, left to right. Stronger acid to weaker acid. I don't know if that's the case for this compound. That charge wants to make me think it's a lot lower than that, but again, very unlikely that shows up on assessment, okay? Last video I'll make for you is going to cover a little bit on Gibbs free energy, review very quickly energy coordinate diagram, which is pretty straightforward, and introduce the last part of that reading, which gets into Zwitter ions and isoelectric effects, okay?